The learning objectives of this chapter are to load and manipulate tensors in PyTorch and send them to different devices like the CPU, the GPU, and the actual tensor processing unit. Then we'll be able to perform basic processing on data, such as standardizing continuous variables as well as categorical variables also. Then you should be able to build a data set out of the tensors. That's after the pre-processing, such as standardization. And you should be able to split the data set into mini batches using data loaders. So we'll talk about tensors, devices, and CUDA. So a scalar is just a single variable, like the value 18. Then a vector is a collection of similar variable. So, and it's just as one dimension. So it's a one-dimensional array of values, like similar to the one you can have in a spreadsheet. So this is how we can create a vector in PyTorch. A matrix is also a collection of values. It's not a scalar, but it's a collection of values. So it's two-dimensional. So it has the numbers of rows, and the number of columns. And for a matrix, each column will be a collection for a particular variable. Like for instance, this is a collection of MPG, this is a collection of cylinders, then this is a collection of the car name. And this is the way we write a matrix as a tensor in PyTorch. So here is the first row. So here is the representing these values here. Here is the second row representing these values here. Then what exactly is tensor? We call a tensor a three-dimensional array of values. Like for instance, we have this spreadsheet here, which is 2D. So if there are a collection of spreadsheets containing data, then we refer to that as a tensor. So how do we create tensor in PyTorch, in Python? For instance, if we want to create an array of ones that has a row of two, that's two rows, and has three columns, here is the syntax for it. So it is an array of one, it has two rows and three columns. You can also initialize random tensors from the PyTorch, using the PyTorch API. So this expression says that you are initializing random tensor. It has three rows. It has four columns, but there are two of them in number. So remember that we are dealing with tensors, and we say that anything that is of higher order, that is a collection of 2D arrays. So this is like a 2D array, this is another 2D array. So this is an actual tensor in itself. And we can get the shape, the size of the tensor using the shape attribute or the size method. So this is the vector we created earlier. To get the shape, we use, or the size, we use this, either the shape or the size method, and it will return the number of elements in that particular vector or in that particular tensor. The same thing with a two-dimensional matrix. So this is one-dimensional, that's why it's a vector, and this is two-dimensional. So this shows that it has 2 rows and 14 columns. When we are tempted to get the size of a scalar, we can see that it's empty. So there is no size of a scalar. Essentially, a scalar is 0D, vector is 1D, matrix is 2D, then when you have stacks of 2D arrays, that will give you 3D. So we can use this diagram to differentiate between a scalar, a vector, matrix, and a tensor. So a scalar is just a single variable, vector is one-dimensional array, a matrix is two-dimensional array, then tensor is a collection or stacks of matrices. So this is a visual representation of a tensor. Now we go to NumPy. So we've been dealing with PyTorch that uses the tensor, that in which we can create different tensors representing different dimensions of array. But we also have a NumPy. So it's NumPy sits at the core of many deep learning libraries such as scikit-learn, pandas, and matplotlib. So we can also the NumPy, it interfaces directly with the tensors that we have in PyTorch. So remember, we're using the PyTorch API or the PyTorch library for this course. So that's why we're dealing with tensors and we are creating tensors that way. But if we were to use other APIs like scikit-learn, the NumPy library is actually synonymous with the tensor library we've been looking at. So in order to convert from a tensor to a NumPy array, it's like I said, it's very compatible. So you first of all have to import the NumPy library. Remember, this variable was a tensor. We defined it as a tensor. So to convert to a NumPy array, we just put the NumPy method here. And when we view the results, you can see that it's now a NumPy array. So similarly, if you want to convert from a NumPy array back to a tensor, all you just need to use is the asTensor method, and you put in the NumPy array inside. As you can see, it's returning a tensor. So this is a tensor and this is a NumPy array. The two of them are doing the same thing. It's just that we are dealing with PyTorch in this course, and as such, it is the tensor we are talking about instead of using the NumPy array. But as we have just seen, the both of them are very compatible, and you can convert from one form to the other. We will now talk about reshaping tensors. For instance, if you have this tensor 2, they are actually 2 in number, so each one of them has 2 rows and 3 columns, and you want to reshape the first tensor such that it just has one row, and the second one you want to convert it also so that it has 1 row. It is possible to do that, and the method in which we use to reshape tensors, we use the view method or the reshape method. So here we created a tensor of ones which has 2 rows and 3 columns, and this tensor we want to reshape it such that it has only 1 row. So we use the .view command and the .view method. So it wants to reshape it to 1 row and 6 columns. So in terms of the diagrams, so this is the original tensor here, and this is the reshaped tensor. So instead of having 2 rows and 3 columns, it just has 1 row and 6 columns. So when we look at it, review it, we can see that this tensor has been reshaped to this particular tensor, and we can see that if there's a very interesting property of reshaping. So it turns out that when you use the view method, to reshape. If you change, like this is the original tensor here and this is the reshape tensor. If to say I change a value in the original tensor, when you go again to view the reshape tensor, you will see that the value has also been changed also in the reshape tensor. So for instance, our original tensor was just 1. It was just a 2D array of 1. This command said I should change, it says that the first row and the second column should be changed to. So, and that change has been effected. But when you now view the reshaped tensor, you can see that it has also changed to a value of 2. So that's the one interesting property of the view method. And it's also the same thing with the numpy. So if remember we created the numpy array, so this command here is to change the last element in the numpy array to 1000. So the element in the numpy array has been changed to, the last element has been changed to 1000. And now, you know, we got this numpy array from this tensor, and when we go ahead to view the contents of this tensor, we can see that it has changed. So this property is similar, it goes with the view method, and it also goes to with when you have created a numpy array from a tensor from numpy array, and when you change one element in any one of it, when you want to view it in either an array or a tensor, you will see that both of them have changed. So in order to avoid this issue, because that might not actually be your intention, to when you are changing something in an array, probably you don't want the other source where you got it from to change, it's better to use the clone method. So here we cloned the original tensor, so and we can view it. Now we can view the clone tensor here. Now we changed the elements in the first row and in the second column to 3. So when we compare the two, we can see that they are different. So if you don't want those changes to be duplicated, it's better to use the clone method. And we'll talk about contiguous tensors. Contiguous tensors simply means that the elements in the same row should be next to each other in memory. So if the elements in the same row for that particular tensor is next to each other in the memory, then we say that it is a contiguous tensor. So given this example, this is a 2 by 3 tensor, and in memory, you look at how the elements are arranged. So we can see that each element in the same row, like for instance, this is one row, there is next to each other in the memory. The elements in this second row, they are also close next to each other in the memory. So but this particular one, which is the transpose form of this, is not a contiguous tensor, because look at these two elements, the white and the orange. They look at the white here and look at the orange, so they don't go, they are not located next to each other in the memory. So this is not a contiguous tensor. So in order for us to see the rules for moving to the next row or column, you can use the stride method. So this is the original tensor and this is the transposed form. So it was this, where did we transpose it? Okay, it's here we did the transpose. So .t is the method in Python to transpose. So when we look at the rules for moving to each row or to each column, so this original tensor gave this and this one gave this. So what this means is that you skip 3 positions to move to the next row in memory, and this one says that is the other way around. So you need to skip 3 positions to move to the next column in memory. So that's the rule that is governing its location in memory. Then in order to check if a tensor is contiguous or not, you use the is contiguous method, uh, which returns if it's a contiguous tensor or not. So when we try to check if this transpose tensor is contiguous, it returns false, and this one returns true. So we can see that you can, in order to you can simply call the contiguous method, and Python will modify the data in such a way that it can be transversed in a typical fashion. So for instance, the transpose tensor we can say is not contiguous because it returns a false. But if you want to force it to be contiguous, then you use the contiguous method, and then you would use the view method how you want it to be reshaped. So this is the original tensor, but once you call this contiguous method, you are saying that you want this particular tensor to go to another memory, and the rearrangement, it has to, you need to force it to become contiguous so that the elements in the same row are next to each other in the memory. So this was the original tensor. This is the transposed form, and when we forced it to be contiguous using this, we can see that the elements in each row are next to each other in the memory. So finally, instead of using the view method like to reshape, you can also use the flatten method instead. But the only difference between the flatten and the view is that in the view you are specifying the number of rows and number of columns, but the flatten will just turn everything into one dimension. So the flatten method will just turn the whole tensor into one dimension. So there is not really any way you can specify the number of rows or the number of columns. Then we have something called named tensors. So why are named tensors? Why are they even there in the first place? So before we actually look at that, we need to understand the concept of broadcasting. So using this example, you have this numpy array here, and you have this scalar here, and we want to multiply a times b. And when we do that, we arrive at this. So when this is multiplied by this to give you this, as we can see. And why is this possible? It's possible in the sense that this is a vector, this is an array, but this is a scalar. So in the background, under the hood, PyTorch or NumPy is just going to do some kind of broadcasting. So it will just spread out this the elements in this particular scalar. It will spread it out to broadcast it so that this is the same number of columns, and the result is that you'll be able to do the multiplication. So for instance, if we have this tensor here, 3 rows, 3 columns, and you want to multiply it by this, the same broadcasting tool, it works. So when we do the multiplication, it returns, the multiplication gives this value. So this 1, 2, 3 is broadcasted, and it's like there's a multiplication across each row, and that's why we are able to do the multiplication. So for instance, now a problem can arise if we mistakenly transpose the second, this mat2, which is like a vector. So where so this is the mat1, this is the mat2, which is like a vector of 1, 2, and 3. So if we mistakenly transpose mat2 and we do multiply it, we can see that it still works, but it was actually a mistake. So in order to solve that, that was why named tensors, that was where they came into play. So in order to name a tensor, you have to say names RC. So after defining the tensor, the elements in the tensor, then you will name it, and you're going to name it, then also the second uh, the second variable of the multiplication too. After defining that particular vector or that particular tensor, then you have to name it, such that after doing this kind of naming, you will still be able to do the multiplication, but we know that is now a named tensor. So if a tensor is named in this fashion, when we try to, if to say we made a mistake and we mistakenly transposed one of them and we try to do the multiplication, we can say that it's going to return an error because of the fact that it has been named. So we have named the rows and we've named the columns. So when it is transposed, it's like the other way around. It now becomes CR. And we know that that's not the order, that's not the correct order. So for instance, we named row and we named it column, we named this row and we named this column. So we are able to do the multiplication because broadcasting was still in place. But now if you mistakenly transpose this, so it's essentially like CR because of the transpose, and that is why if you try to do the multiplication, it's not going to be successful. And it turns out that you can this named tensors, it works only if both tensors are named, and if one of them is not named, broadcasting is going to work as expected, as we can see. So we'll go to devices. So far the tensors we've been creating, they are CPU tensors. It means that the tensors are stored in the computer's main memory, and any operation performed are handled by the CPU. So if we use this command to check the type of device we are using, we can see that it's going to return a CPU. And but we understand that GPU, they are much more powerful too, especially for our deep learning application. And originally the GPU were not designed to work with deep learning. They were just designed for gamers. It was NVIDIA's release of CUDA, which stands for Compute Unified Device Architecture, and later AMD ROCm, that allowed deep learning frameworks to easily interface with the GPU. So in order to check, or in order to make use of the GPU instead of the CPU, we can call this PyTorch command, torch.coda is available. And when we call this command, we are saying that is there any GPU available. So if not, if it's available, then we use the GPU, but if not, we'll still return to the CPU. So you can send your tensors to that particular device. That's in the case, because by default it's a CPU, but using this command, you can change to GPU. That's if you have one, and you can send your tensors to the GPU so that it is the GPU that is handling all the complex tasks of that has to do with that tensor. So you can also use this command here. So if you have multiple GPUs on your computer, you can use this command here to name them, and you send it to the, and afterwards you can send the tensor to a GPU. And once you've sent the tensor to a GPU, it cannot be brought back to numpy anymore. So this tensor here, it has been sent to the GPU. So in order to bring it back to the CPU, you have to use the .cpu command, and then we know that it has access, the tensor has access to the CPU. Then aside from the GPU, we also have TPU. TPU stand for Tensor Processing Unit, and they were designed by Google to allow for the training of deep learning models in TensorFlow. And they are available on Google Colab, which we are using, and on Kaggle, but it's not free. If you actually want to use the TPU, it's not free in Google Colab anymore, but you can use it to speed up the training by using all cores at once through multiprocessing. So through the use of the TPUs, but we are going to be using the GPU because the TPU is not available for free in Google Colab. So it's the CPU and the GPU that it's possible for us to use. So we now go to the last set of device, which is called meta or fake device. So this meta device, we normally use it to load a model from disk, and especially when we want to create an instance of the untrained model first. So you load the model into the meta device. So this is a command to create to load this tensor, which has 2 rows and 3 columns, to load it into a meta or fake device. So when we try to view it, we can see that it's the tensor has been created, but it doesn't contain any data. You know that here we said it should have it should be an array, a 2D array of ones, but when we try to view it, it's a fake device, so it doesn't really contain any data, but it's just imaginary and it's there in memory. So when we try to create this tensor that it's 100,000 by 100,000 using the fake device, the meta device, you can see that the tensor has actually been created, but it has no content. If we were to perform the same operation now without loading it on the meta or fake device, we will see that it would, this operation, you can just try it, it's not going to work unless your computer has up to 40 gigabytes of free RAM. Eventually it's going to give you an error. So fake tensors or meta tensors are useful to handle tensors and models that are too large to fit in the memory, but we won't be using fake tensors or meta tensors in this course because our scope is not because of our scope. But just be aware that when you really venture into large models, then you are aware of your options. So the options we've presented are the meta devices, the TPU devices, the GPU devices, and of course the CPU device, which is by default. Now we'll go to the data set. So we have this data set of AutoMPG dataset from UCI machine learning repository. So this is a view of the dataset here. So it's the AutoMPG data cells data set, and the data set has different columns: the MPG, cylinders, displacements, horsepower. So this stands for MPG, cylinders, displacement, horsepower, AC. And the MPG is continuous. It's a continuous value. It's a continuous variable, as you'll be seeing later. The cylinder is discrete. Is categorical variable. So the last one is the car name, and it's unique for each instance. So as you can see here, this is the car name. So what this data set does is that for different cars and for different features like uh, cylinders, the year of the manufacture, the origin, where it was made, displacement, then you measure the fuel consumption, which is on this row representing the miles per gallon. So that's what this data set is all about. So we want to be able to explore the data sets. We want to be able to do some pre-processing, and we want to be able to arrange it so that we're able to eventually fit it into our deep learning model. So that's what we are going to be doing for the remainder of this lecture. So we want to load the data. So this data is actually is comma separated, or let me say space separated. So the values are space separated or tab separated or comma separated. So in order to load it, we'll use the pandas. We'll import pandas as PD. Then we get the data set from this URL. Then the column names, we have specified it. So each of the columns, this is miles per gallon, this is cylinder, displacement, horsepower, weight, acceleration, the year, the model year, and the origin. So the origin. So we are not going to load the car name because it's not numeric. So our deep learning model, the first one will start with all of these numbers, but this is not a number, so we are not going to load it because we are dealing with numeric data. So after getting specifying the column names, then this is the variable that we're going to load it into. So we'll call the PD and we call the read CSV. So we'll say that it should read the contents of the data from this URL, assigning these column names, and if there are missing values, it should or question mark, because this data set has some missing values. So question mark. So where there's no value, it's question mark. So what that line is saying is that any question mark is it's a missing value, then it's space separated. So to go to another column, is should you use the space separator. And when we do that and try to view the variable df, we can see that we can see the old data. So the data has 379 rows and 8 columns. That is the data set we have loaded into the pandas data frame. So the pandas data frame df can be sliced column wise or row wise. We can retrieve individual columns. For instance, if we want to view the MPG column here, which is the first one, you just call it with a column name and you'll be able to view it. And also, if you the Panda series work as a wrapper around underlying numpy array. So if you want to view the first 5 values on the MPG column, we use this command and it returns a numpy array that contains the particular data. So the data is retrieved using the value and is retrieved as a numpy array. So you can also view or select multiple columns within a slice data frame. For instance, if you want to view the MPG and the horsepower column, we use this specification and we have the MPG and horsepower column. So you can also retrieve the numpy array. For instance, now we want to get the first 5 values of the MPG and horsepower column. So we use the values attribute. So it's going to return the values as a numpy array. So in order to get a subset of the data frame, like you just for all of the data set you have put into your pandas data frame, you just want to get the first 5 values. Then you use this iloc attribute. So you get the first 5 values. I should say here that for Python, the indexing starts from 0. So we're getting the first 5 values. So the indexing starts from 0. So 0, 1, 2, 3, 4. And it's also possible to use Boolean series to subset the rows in a data frame. So for instance, the year, we are looking at the year column, but we want to retrieve this only if the values in this column are equal to 70. Then you should just retrieve, all the values that are equal to 70, then you should put it inside this variable. Then you know this is the data frame for the whole data set. So when we use this command, the data set that will be shown is only the data set in which the year is going to go through the whole data set, and is only that in which the year is 70, 1970 to be precise. So that's what it returns. So you can subset specific data frames in your data set based on some conditions. Then we go to train, validation, and test weights. As I've told you earlier, it is not all the old data we have that we are going to feed into our AI model. So we need to divide the data into training, validation, and test set. So the training set is used to train your model, and it is this data that the AI sees. It is this data that your model sees and uses in order to develop the full-blown AI model. At the validation set, the AI model sees it, but it uses it to tune the hyperparameters and just to make slight adjustments to the AI model. Then the test set, the AI model that's been developed has not seen it. It has only seen it just once, and that is when it uses it to make the prediction, and it is only that time it has seen the test data set. So before we divide the data into train, validation, and test, we need to shuffle. Why do we need to shuffle? If we use this command here, so here is the data frame of the whole data set, just the year column, the first 50 values, we can see that they follow a sequential form. So even if we look at the sheet, the CSV sheet, it follows a sequential form: 70, 71, then it goes to 72, 73, 76, and we don't, now we want to split the data set into train, validation, and test. If we just do the splitting straight up without shuffling, then the train data set that our AI model will use, it will not be very robust because it needs to see a mix of all the varieties in the data set. So probably, like I said, the column here, it was following a sequential form. It started from 70 and it ended at 1982. So we want all of these years to be in all our three sets. So if to say we do not shuffle, probably some years will be missing in in one or two or even three of all the sets, of all the three sets. So in order to really achieve this, we have to shuffle. And how do we shuffle? We use the sample method, and this is the one that actually does the shuffling. And after shuffling, then we can now split. So we use the circle uh, library, and we would import the train test split. So this line here is to split it into training and validation and test. So you can see that the test size will be 16%, while the training and validation will be around 84%. Then after that, we'll split the training and validation into uh, train and validation. So the validation size is 20%. Then the training set should be about 64 uh, should be about 64%. So this is the command we use to split. Then after that, we need to clean the data. So we need to undo missing values. So as I've shown you earlier, there are some missing values in the data set, and if we have missing values, the AI model doesn't understand what a missing value is, and there are some methods we can use to replace those missing values, but for now we'll just remove them. So these are the commands to remove the missing values from the training set. So this command, it has shown us the missing values that is in the train set. Then it is actually this command that would remove all the missing values in the training set. So likewise, we should remove the missing values in the validation set, and we are removing the missing values in the test set, such that our AI model will not be disturbed by those missing values. And now, so we are done with cleaning, so removing the missing values. So now we want to do some pre-processing on the data. So when we started on the data aspect, I said that we had our continuous attributes. and we had uh, categorical or discrete attributes. So the continuous attributes we have in our data set are the miles per gallon, displacement, horsepower, weight, and acceleration, because they have a numeric value. So, and they are these values are in the continuum. So they are not like categorically, they are not categorical in the sense that they are not this, that, or this. They don't fall into uh, any particular distinct set of category. So we call them continuous attributes. So we want to be able to look at these continuous attributes in this data set and do some pre-processing on them. Then later we look at the categorical or discrete attributes that are in the data set and also perform some pre-processing on them. So the first thing is that we create this variable for the continuous attributes. Then we'll try to uh, get it using the train. So this command gets all the continuous attributes, then gives a name to it, and we call it the train features. And here we are looking at the histogram of all the continuous attributes in the data set. So this is the histogram of the displacement, the horsepower, the weight, and the acceleration. This this step we've just done is really very important, and it is powerful, because from the visualization we are able to see the spread of values of these continuous attributes. For instance, we can see that for the displacement, it started maybe between 50 and ended at about 450. So these are the values, different values we have there. For each of them, this is the frequency, that's on the y-axis, the frequency at which they occur. Also the horsepower, it started from about 20, ended at about let's say 250, and the weight, it's between 1000 and 5000, and the acceleration is between, let's say, between 5 and 25. So this is not good for deep learning. Why is it not good? You can see that the range of values, they are different. So this one is from 100 to 400, 50 to 200, 2000, which is like on a different scale. So the keyword is the scale. Each of these continuous attributes have different scales. They are not within the same brackets. They are not within the same numeric brackets. So this is between 50 and 250. This is between 2000 and 5000. This one is even between 5 and 25. So they are not within the same brackets. So it turns out that this, if we were to feed these attributes directly into the AI model without doing some form of pre-processing, the deep learning model wouldn't really be optimal. And it has been shown that it is when these attributes are within symmetrical values, and preferably if they are actually low, and if they are within the same range, probably from -3 to +3, that's when the AI model will be really good, and our AI model would exhibit less problematic behavior during training, and our AI model would actually converge to a good solution, to the optimal solution. But if we work according to this scale, it's going to be very problematic, and we don't really be able to converge to a good solution for the prediction. So one method we can use, because now we want to put all of these continuous attributes within the same scale. So one method we use is called standardization or normalization, and this is the formula for the standardization. So for each of these attributes, so you get the mean and you get the standard deviation. So you subtract it the 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 column, the data set, you subtract it from the mean and you divide by the standard deviation. So when we do that, we say that we've standardized the data set. So here is the formula to calculate the mean. Here is the formula to calculate the standard deviation. So we can see the mean and the standard deviation of each of these continuous attributes. Remember that there are 4 in number. So now we want to standardize. So we'll subtract from the mean. After that, we divide by the standard deviation. So that's what we've done here, and that is what is in this equation here. After we do that, we now find this line here. This line here is to find the mean after standardization and to find the standard deviation after standardization. So when we check the mean again after we have standardized, this is important, after we standardize, we can see that the mean is about 0 because exponential minus 16 is close to 0. So the mean is close to 0 and the standard deviation is equal to 1. That's what we call standardization. So we've made the whole continuous attribute. We've tried to make it to be in the same scale. Remember, before we standardized, we looked at the mean, we looked at the standard deviation. They were just varying. They were not within the same range, and the standard deviation, all of them were just on a different scale. But now we've been able to standardize. So in order to confirm, let's look at the histogram now of the continuous attributes after standardization. We can see that now the values is between -1 and 2. Okay, it's between 0 and 2, -1 and 2, -2 and 2. So these attributes are now on the same scale. But have we actually changed these attributes? No. And the reason why it's no is that if you look at the shape, of this histogram, it is still the same shape. It's just that the values have just been standardized, as the name implies. So we are doing a very important pre-processing step here. So now, previously we standardized the training sets. So obviously too, we need to standardize the validation, the attributes of the validation set, and we need to standardize the test set too. But note that the standardization of the validation set is the mean of the training set and the standard deviation of the training set you will use for both the validation and for both the test. So you are not using the mean of the validation set. You're using the mean and the standard deviation of the training set. And even if you do that, you would see that it is standardized appropriately. So we have to standardize both the validation and the test set. So instead of going through all those maths and all those code, there's a feature in Python and a scikit-learn, so the standard scalar. So you can just simply import the standard scalar and you use it. Once you import the standard scalar, then you define the scalar, then use the scalar on your train set, then it would automatically standardize your train set. So instead of going through all those maths, so here is to standardize the validation set and the test set. So in order to better streamline the process, you can also write a standardized function. And what the standardized function will do is that it will take the data frame consisting of the data set of the values, of all the values you have, then it's going to create and train a standard scalar if one is not provided, and it will return a Python sensor containing standardized features and an instance of the scikit-learn standard scalar. So this is the function that actually uh, so this is the function that has been created to do that. So using this function, you can call the method, the this function that you've defined here, you can call it and you can use it to do the standardization. So different methods of doing standardization we have discussed. Now we go into the other kinds of attributes. We've talked about the continuous attributes. Now we want to look at the categorical attributes, how to preprocess it, because though both of them are numeric, but given that their structure is different, we need to preprocess it in a different manner. So the first categorical attribute is the cylinder. So the cylinder, the year, and the origin. These are the discrete or categorical attributes we want. And we performed a standardization on the continuous attributes. So we would do a kind of preprocessing to make the model optimal so that it converges to a good solution. So we are going to do the preprocessing on the discrete or categorical attributes. So one thing we'll first do is that we'll look at the cylinder attribute, which is a discrete attribute, and get the unique values, because we want to be sure, is it really discrete, is it really categorical. And when we look at the cylinder attribute, so let me go to the original one. This is the column for the cylinder. So why are we even calling it discrete or categorical? So when we look at the unique values are the range of values that are unique to that particular column. We can say that this column contains only 3, 4, 5, 6, and 8. So it's discrete. It's just how many categories? 5 categories. Let's look at the year column, and let's look at the discrete. Let's look at the unique values. It just contains values from 70 to 82. That is about 13 unique values. So that's why we call it categorical discrete. It just has 13 discrete values. Let's look at the origin. The origin attribute. It just has 3 unique values. So these values are indeed discrete, they are indeed categorical, and they are different from the continuous variable. We have to preprocess them differently such that our AI model converges to a good solution. So we can build a dictionary to map them into sequential numbers. So we already know the unique values. So this line of code will just map them to sequential numbers. So this is 0, 1, 2, 3, 4. So we've done that here. So another thing we can do is that we can, in place of, we're looking at the cylinders now. So in place of those values, we can come up with a lookup table, and that lookup table would represent the weights that, or will represent a kind of synonymous representation. Instead of those discrete value, we can just say that these are the weights, or these are the values that would represent them. So for instance, we came up with this table, and these values were generated randomly. So for this, these are the weights for the first one, which is 3, because we are talking about the cylinder attributes. So this is the weight for 4, 5, 6. So this is the weight for 3, 4, 5, 6, 7. So because we have, okay, 3, 4, 5, 6, 8. So these are the weights for 3, 4, 5, 6, and 8. So we can use this method as a form of mapping dictionary, so that we know that these values, maybe they had the random weights that will first of all initialize to represent um, the discrete value of the weight. And for instance, if you want to look up 6 now, the data set or the unique value of 6. So remember, this one represents 3, 4, 5, 6, 8. So you can use this code, and the and we can use this mapping. So this can be used to map to a sequence. So this is a sequence of 8 numerical values that maps to the number of cylinder, which is 6. So this is one method. And another method is, instead of generating this random table, you can import such as as neural network, then call this embedding class. So this embedding class will essentially do what we've done previously. And what have we done previously? We created a sequence of numbers that map to a particular cylinder value. So what this does is that it has created a sequence of numbers that map to a particular cylinder value, such that if you want to retrieve a particular sequence for maybe 6 cylinders, so this is what it's returned. So these are randomly generated. So obviously we have different random numbers since we used a different approach. So another thing we can do is called the one-hot encoding. So it's another form of encoding in which we'll just also create a sequence of values where we just map each sequence to each discrete value of that particular column. So for instance, if we want to look up the one for cylinder number 6, then this is it. So apart, for the continuous attributes, we used the standard scalar where we got the mean, then we divided by the standard deviation. Our scikit-learn also has something for the categorical or discrete attributes. So it's called the ordinary encoder. So we'll do the same thing. We'll put the ordinary encoder. They would create a variable consisting of our discrete or categorical attributes. Then we initialize the encoder, and try to fit the encoder to the data set we have, which is the train set. So when we do this, what it actually does is that instead of us using those particular discrete numbers, it creates an index. It's using the index of those numbers. I don't know if you understand. So let me explain it from this point. So here we got the unique values for the cylinder, we got the unique values for the year, we got the unique values for the origin. So instead of using these particular values, remember we are trying to do some pre-processing. So instead of using these values and just putting it straight up into our AI model, we use the index of the values. So this is indexed as 0, 1, 2, 3, 4. 0, 1, 2, 3, 12, up to 12, 0, 1, 2. So it is the index we are using, and we are going to feed into the AI model. So what this encoder, ordinal encoder does is that after we just put in the features, the discrete or categorical features into the encoder, it returns the index. It gets all the unique values and returns the index. So instead of those values, actually it is the index it returns, and it's that index that we are going to use and we are going to feed into our AI model. So it's a kind of preprocessing that we are doing on the discrete or categorical value. So it is different from the preprocessing you do on the continuous attribute. So based on our preprocessing now, we look at the discrete attribute. They want to get the specific. If you actually want to retrieve the specific values, then you use the iloc command. So the iloc command is going to retrieve the specific values. So this is a form of preprocessing and is the ordinal encoder. So in the case of the continuous variables, in which we developed a standardized method. So we developed an encode method too that actually does something similar. So we take in the pandas data frame and a list of columns that are categorical. Then it would create and train a circuit ordinal class. So we'll call the ordinal encoder. Then it would return a Python sensor containing the encoded categorical features. So it returns the encoded categorical features. So it's called the ordinal encoder because we are kind of encoding. We have the original values, but we're just trying to do a kind of encoding, and we've said the reason why that kind of encoding is necessary, because of we want our AI model to get a optimal solution. So we do that. We encode the training set, we encode the validation set, and we encode the test set. So the resulting features are indices now, but it is possible to retrieve the original values, and we use these values to retrieve their embeddings. So because we did two kind of embeddings, so one is the ordinary encoder, then one is just a kind of sequence of numbers that map to a specific discrete category. Then we are moving on to the last lab, which is we are trying to see if we can actually feed all of this preprocessing to our AI model. So we'll talk about the target. We have already explained target to you. I said target in machine learning is the output. So we need to look at what is the output and what are the features. So we are going to start with a very simple linear regression task. So we just want just one attribute and just one target. And the attribute that we're going to be using is the horsepower. So we've already standardized it. So that's the horsepower we're using. We're not using any discrete or categorical attributes. And the target is the miles per gallon. So basically in this data set here, so these are the features. Then based on the features, what is the fuel consumption in miles per gallon? So this is actually the target. In other words, this is the output. So based on all of these features, we want to predict the output, the miles per gallon that the car is able to travel. interval. So we've picked the 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 attribute we want to use. We want to use just a single feature for now. Then we've picked the target, which is the mass per gallon. So now we'll now go ahead and develop a tensor data set from that. So the we have the we have the this is the output and we have the input. So the input has been standardized. So we now want to do a visualization now of this. So this is the feature, this is the horsepower, and this is the output, this is the target, this is the fuel consumption in miles per gallon. So this is a visualization of our inputs and our output. We can see that the relationship is not quite linear, but we can see that there is a correlation between the car's power and its fuel consumption. So the correlation we can see is that the more powerful the car is in terms of horsepower, the less fuel efficient it's going to be. So the less powerful, the more fuel efficient the car is going to be. So now we've done all this pre-processing. The next step is to build a tensor data set. So we have two tensors now, one for the attributes and one for the target. So we just combine them to a tensor data set, and that's just the process of combining the attributes with the target. So we would import the tensor data set, we put in the attributes and we put in the targets, and now we have our data set pipe. So from the data set pipe, it's essential because you can, after developing the tensor data set, you have the you can use lots of methods, like you can get the length, you can get the item, so you can perform lots of operations on the tensor data set that you've built. So you can get, here we're getting the first 5 values. Then also we build the tensor data set of the validation and the tensor data set of the test set. And now the next step, which is the final step for this class, is to build mini batches, because we are here. We want to load the data now into the AI model. And it turns out that mini batches are 32, 64, and 128. So they are usually a power of 2. So we'll build the data, the mini data batches. So the data loader is a rich class and it has many parameters. So the data sets you have, then the batch size, which is a power of 2, then drop last. Drop last simply means that if you know it's in the batch size is always a power of 2. So if the last batch doesn't add up to sum up to the batch size, then you just drop it. Then shuffle, we want some randomness uh, inside. So you build the mini data set loader. So we can see a batch size now of the attributes and a batch size of the target. So we've been able to do all of this in this particular class. So hopefully we've been able to achieve all of these aims and all of these objectives.